Hi guys, today we will continue with the another two operations on the graph. That is, one is a connected components and another one is a spanning tree. Already we have completed the traversal by using a BFS and the DFS algorithm. Now we will start with the connected components. So before finding out the connected components, we will see the definition of a connected graph. So already you know the definition of a connected graph. So if it is possible to get from every vertex in the graph to every other vertex, that we call it as a connected graph. Like for example, if you see, this is a graph you have. If you consider the first graph, now let us see that whether it is a connected or not. How to say it is a connected is, from the vertex 0 you are able to reach to 2, you are able to reach to 1, and you are able to reach to 3. And similarly from 1 you are able to go to 2, you are able to go to 0, and you are able to go to 3. That means from one vertex, if you are able to reach to another, all the other vertices, that we call it as a connected graph. So that is the meaning of this definition, connected graph. For from a particular vertex, if you are able to reach the remaining vertices, that is a connected. Now let us see here, we have to find out what are the connected components here. So for example, if you see from 0, this is completely is a one graph here. This is one graph. What are the components, what are the vertices you have? 0, 1, 2, 3 and 4. These are the vertices you have. Now here we have to see whether it is a connected graph. Is it connected? No. From 0 you are not able to reach to 3, or from 0 you are not able to reach to 4. And so this is not a connected graph. So here this particular graph is having two components here, two connected components. This is one component and this is another component. What is in the first component? What are the vertices you have? 0, 1, 2 are the first component. This is one part of the graph. And what is another one you have? 3, 4. So this is a not a connected graph. Since it is not a connected graph, how many components you have? We have here two components we have. Now here we have an algorithm for finding out the connected components, or to find out whether it is a connected graph or not. So it's very simple. You can call the BFS algorithm or DFS algorithm to say that it is a connected or not. So here we have a graph here. This complete thing is a single graph. Now how many vertices you have? You have from 0 to 7. So we have to check whether this graph is a connected or not. So just now I gave you the definition what is meant by a connected graph. So what is the definition? From every vertex, if you are able to reach to all the vertices, that is a connected graph. So this is a graph given. So by using the algorithm, we will check whether this graph is a connected graph or not. Now I said either we can use a BFS algorithm or DFS algorithm, but here we will be using, I'm using the DFS algorithm. So this is the algorithm you have. The connected is an algorithm name, and from 0 to n. 0 to n means from the first vertex to the last vertex, from 0 to 7, the process should be repeated. If not visited, if a particular vertex is not visited, you are calling the DFS algorithm. Initially, all the visited values will be 0. Already we have seen in the DFS algorithm. We will be initializing with 0. Initializing with 0 means not visited. If it is 1, it is visited. Please you refer the previous video for that. Okay, we will start with an example. Now first I equal to 0 I have started. Now this is a graph what we have. So first for I equal to 0, and I am calling the algorithm DFS. So for DFS, the data structure you will be considering is a stack data structure, and for BFS we will be considering the queue data structure. Now here we will be considering the stack data structure here. So first we have started with I equal to 0. Now if not visited of 0, so initially I said all the values are 0, visited of 0 to so on, visited of 7 is 0. That means no vertex has been visited up to now. So it is true. First we have started with I equal to 0 to 8. So I equal to 0, visited of 0 equal to 0, true, because it is initially not visited. So what you are doing now, since it is true, you are calling the DFS algorithm first for I equal to 0. So already you know the DFS algorithm. So this is the DFS algorithm. Already in the last video I have shown you how to trace out the DFS algorithm. The same thing I am showing you again here. So first, now I am calling DFS of 0. Now what we are doing now, you keep the DFS algorithm side and you just check it. So what we are doing now, we are making 1, that means the 0th vertex we are visiting, and you are writing 0, and this 0 you are entering into the stack now. Now all the adjacent vertex of 0 you are taking now. What is adjacent vertex of 0? That is, adjacent vertex of 0 is 1 and 2, and the ascending order it is 1. So 1, adjacent vertex of 0 is 1. Visited of 1 is 0. Yes, it is 0, true. So since it is true, now you are calling the DFS, and you are writing 1, and 1 you are pushing onto the stack. Now again we will check for adjacent vertex of 1. What is adjacent vertex of 1? It is 3. So adjacent vertex of 1 is 3. Now visited of 3 is 0. We have initialized it, right? So it is 3. It is true. So again you are calling DFS of 3 and you are writing 3. So 3 is pushed onto the stack now. Now again, adjacent vertex of 3. What is adjacent vertex of 3? It is 2. So again it is, adjacent vertex of 3 is 2. It is 0, true. So you are calling the DFS of 2 and you are writing 2 onto the stack. Now adjacent vertex of 2. Adjacent vertex of 2 is 0. It is 0, but it is 1. So it is becoming false. So since it is becoming false, you will be removing from the stack now. So next what you have? 3. So adjacent vertex of 3. Adjacent of vertex of 3 is 1. So 1 is already visited. 1 is already visited. So this is also becoming false. So 3 is removed now. Now next, adjacent vertex of 1. It is 0. This is also visited. So this is also becoming false. And so 1 is also removed. Next what you have? Adjacent vertex of 0. It is 1. So it is 1 is already visited, so that will also be removed. So now the stack is becoming empty. So with this we have completed iteration, first iteration I equal to 0. Now we have to start with I equal to 1. So it is not required, the same process will be repeated for I equal to 1, I equal to 2, so on. But the thing here is, the algorithm is terminating without visiting the vertices 4, 5, 6, 7. Whatever number of iterations you do, we are not able to visit these vertices 4, 5, 6, 7. The meaning is, from 0 you are not able to visit this, from 1 also you are not able to visit this. That means the graph is a not connected graph. Since it is not connected graph, and if you are able to observe here, we have two components here. Two components you have. In the first component you have is 0, 1, 2, 3, and in the second component you have is 4, 5, 6, 7. These are the two components you have. That is about the algorithm connected components. Either you can call the BFS or DFS here. It's simple. Now we are moving to the next operation, that is about the spanning trees. So here what is meant by a spanning tree? This is a graph. So graph, already I said, the graph consists of set of vertices and edges, and if you observe, it is closed. It is closed. And coming to the tree, the difference between, now here our concept is a tree here, spanning tree. So what is a tree is, it is open. The difference between a graph and a tree is, a graph is closed but the tree is open. So here, if you observe here, A, B, C, D, here also we have vertices, but if you observe, it is not closed. It is not closed, not closed. So these are the three trees you have. So that is the difference between a graph and a tree. Tree is closed. If you see, it is closed here, but it is not closed. It is tree. And it is a subgraph. It is a subgraph of the graph, because we don't have all the edges in this. It is a subgraph. Now, what is the difference between this tree and a spanning tree? In the spanning tree, whatever the vertices you have in the graph, all the vertices you will be having in the spanning tree. A, B, C, D are the 4 vertices you have. In the spanning tree also you will be having the 4 vertices. 4 vertices you will be having. That is a spanning tree now. So spanning tree of an undirected graph is a subgraph, that is a tree in which includes all the vertices of G with minimum possible number of edges. I said, right? So all the edges, all the vertices, whatever you have in the graph, all the vertices you should have in the tree also. That is a spanning tree. Now here we have 2 types of spanning tree. One is depth first search spanning tree, DFS spanning tree, and another spanning tree you have is a BFS spanning tree. Algorithm is same algorithm for the DFS spanning tree and the BFS spanning tree. Already we know the DFS you will be considering the stack, for BFS you will be considering the queue here. So now I will show you how to draw the spanning tree using the DFS algorithm. So this is the graph we have. For this graph we have to draw the spanning tree by using the DFS. So we can start from any vertex, but I am starting from 0 here. So 0. First I am visiting 0. I have taken the vertex here. Now this 0 I am entering into the stack. This 0 I am entering into the stack. Now the next step. What are the adjacent vertices of 0, 1 and 2? In the stack you will be considering only one adjacent vertex. So in the ascending order 1. Now 1 I am entering into the stack. So whatever you have here, the same thing I am drawing here. Now who is in the stack top? 1. Now 1 adjacent vertex is 3. So 1 adjacent vertex is 3. Now 3 is entered into the stack. So the figure how you have in the graph, the same figure I have drawn here. Now who is on the stack top? 3. Now 3 adjacent vertex is 7. Now 7 is coming on to the stack top. 7. Now 7 is on the stack. Now 7 adjacent vertexes are 4, 5, 6. 3 you have, but only 1 you have to consider, that too in the ascending. So what you have here? 4. So 4 will be pushed onto the stack now. 4 is pushed onto the stack. How you have the figure? In the same way I have drawing here. Now next, who is on the stack top? 4. Now 4 adjacent vertices are 1. If I take this, the mean 1 already we have visited. 1 is already visited. So we should not consider. Now 4 should be popped out now. So 4 adjacent vertex is 1. 1 is already visited. So now 4 you are popping out from the stack. So after popping out from the stack, now next what is the stack top? You have 7. 7 is a stack top. Now 7 adjacent. 7 adjacent you have is a 5 and 6. 4 already we have visited. 5 and 6. But only 1 you have to consider. Now I am considering 5. 5. I am drawing the vertex edge here. Now the 5 adjacent. 5 adjacent are 2. So 5 adjacent is 2. So 2 I am drawing. Taking into the stack, and I am taking the edge here. Now the 2 adjacent. What is the 2 adjacent? 6. 0 and 6. 0 is already visited, and now we have to take 6 here. So take 6. 6. Now is the stack top? 6. So 6 is a stack top. Adjacent vertices are 2 and 7, but 2 and 7 are already visited. So now you remove 6 from the stack. So removing 6 from the stack. Now next what you have? 2. So 2 adjacent vertices are 0, 5 and 6. Already they are visited. So pop out 2 from the stack. Pop 2 from the stack. Now next you have is 5. So 5 adjacent is 2 and 7. So 2 and 7 are also visited. So pop out 5. Pop out 5. So next one you have is 7. So 7 adjacent are 3, 4, 5, 6. Already they are visited. So pop out 7. Now next 3. 3 adjacent vertices are 1 and 7. Already visited. So pop 3. Pop 3. Now next is 1. So 1 adjacent vertices are 3 and 4. Already visited. So pop out 1. So next you have is 0. So 0 adjacent vertices are 1 and 2. Already visited, so pop out 0. Now the stack is empty. So now you have to stop. So this is our tree. This is our tree here. If you observe, this is a spanning tree, what you are getting by using the DFS algorithm. Whatever the vertices you have in your graph, all the vertices you will be getting here. And one more property, if you see here, how many vertices you have? 8 vertices you have, and you will be having 7 edges. Let us see here, do we have 7 or not? 1 2 3 4 5 6 7. 7 edges, 8 vertices, and the number of edges will be n minus 1. This is the DFS algorithm. Using the DFS, we are drawing the spanning tree. Now let us come to BFS. So for BFS, already we know we have to consider the Q data structure. So Q data structure, the same tree I have considered here. So I have starting with 0, BFS of 0. 0 I have taken into the Q now. So what are the, I am taking the vertex. Now what are the adjacent vertices of 0, 1 and 2? So 1 and 2 I have taken into the Q and I have drawn the figure and 2. Now next, who is in the Q now? 1. What are the adjacent vertices of 1? 3 and 4. So take 3 and 4 and take the figure 4. Now 1 is completed. Now next one you have in the Q is 2. Now what are the adjacent vertices of 2? 5 and 6. So take 5 and 6 into the Q and we are taking. So 2 is finished. Now next you have is 3. So 3 adjacent vertices are 7. So take 7. 7. Now 3 is finished. Now next 4. 4 adjacent vertices are, what are the 4 adjacent vertices? 1 and 7. So 1 and 7 already we have visited. 1 and 7 already visited. So next what you have? 5. So 5 adjacent vertices are 7 and 2. So 7 and 2 also visited. So remove 5. Now 6. 6 adjacent vertices are 2 and 7. So that also visited. So remove 6. So next 7. What are the 7 adjacent vertices? 3, 4, 5, 6. So already visited. Remove. So removing from the Q. So now finally the Q is empty. So this is the spanning tree by using BFS. And here also if you observe, we have all the vertices. We have n equal to 8 vertices, and how many edges you have? 1 2 3 4 5 6 7. The number of edges are 7. This is a property you have to remember for the spanning tree. That's all. This is about the topic elementary graph operations.